video is the second part on PD modeling using neural networks and particularly using traditional long short-term memory and quantum long short-term memory. PD projections are very important for decision making to measure the impact on provision, profits, and capital of financial institutions. For example, let's talk about default rate expectation in Europe and US. Speculative grade default rates expected to rise towards 5.5% in Europe and reach 6% in the US. According to Moody's, as of August of this year, default rates are now sitting at 3% in Europe and 4.8% in the US. We expect to see a rise of 2.5% in Europe next year and just a 1.2% rise in the US. We have been seeing more default registered in the US thus far, and the landscape in the US is becoming less pessimistic, with a soft landing looking more likely than in Europe. We expect default rates will rise in both Europe and the US in 2024 for some time now. Struggling companies have been kept afloat with the help of cheap funding, large government and central bank support, and economic strength. But we expect many of them will not be able to endure for much longer if this support is taken away. We believe the following factors will drive this increase: higher for longer rates, less availability of credit, worsening economic environment, lack of government, changing landscape for certain sectors, pressure on metrics, delayed reaction to widening and volatile spreads. Traditionally, banks have used econometric models to make projections. But what is econometric models? Well, econometrics is the quantitative application of statistical and mathematical models using data to develop theories or test existing hypotheses in economics and to forecast future trends from historical data. However, a few years ago, the use of machine learning models began to arouse interest. For other way, machine learning is a method of data modeling that provides the ability to automatically learn and improve the analytical model building. It is a branch of artificial intelligence based on the idea that systems can learn from data, identify patterns, and make decisions with minimal human intervention. Econometrics has been emphasized more on hypothesis testing and causality identification. In contrast, machine learning aims at prediction and has impressive success. In the stage of model design, we shall communicate factors that identify causality. In the stage of estimation, we shall adopt the machine learning method that can achieve the highest level of prediction accuracy. The balance between the two goals can help ensuring the overall project success. From my point of view, it's the best to use both disciplines to create models, econometric and machine learning, for financial risk management. I remind you that in the previous video we used both econometric techniques to understand the relationship of the variables and machine learning to ensure the accuracy of the prediction. In addition, we talk about quantum computing and the importance it will have in the future. Quantum computing is a new approach to calculation that uses principles of fundamental physics to solve extremely complex problems very quickly. Digital computers have been making it easier for us to process information for decades, but quantum computers are poised to take computing to a whole new level. Quantum computers represent a completely new approach to computing, and while they won't replace today's computers, by using the principles of quantum physics, they will be able to solve very complex statistical problems and today computers cannot. Quantum computing has so much potential. For example, quantum computing alone, just one of three main areas of emerging quantum technology, could account for nearly 1.3 trillions in value by 2035. This is the future. Size in Jupyter Notebook, we use a database which we explained in detail in the previous video. I leave the link so that you can see it. The objective of the exercise is to perform PD projection with a traditional recurrent neural network model called long short-term memory and a quantum long short-term memory model using quantum computing. It's worth mentioning that in this exercise we will not use a quantum computer, but a digital computer. However, we will use quantum algorithms such as variational quantum circuits. Also mention that we will use a hybrid model that combines classical machine learning and quantum machine learning. So let's get started. Long short-term memory is a type of recurrent network that is specifically designed to handle sequential data such as time series, speech, and text. Long short-term memory networks are capable of learning long-term dependency in sequential data, which make them well suited for tasks such as language translation, speech recognition, and time series forecasting. In this graph, illustrate the underlying working mechanism of a long short-term memory neural network. A long short-term memory neural network consists of a series of LSTM cells, H0, H1, and HT, that are time series data samples that are fed into different LSTM cells simultaneously as inputs. Introduction. Long short-term memory is a recurrent neural network applicable to a broad range of problems, aiming to analyze or classify sequential data. Great risk modelers have used long short-term memory to predict the PD based on the historical data sequences with great success. Recent studies have shown that the LSTM's efficiency and trainability can be improved by replacing some of the layers in the LSTM with variational quantum layers, thus making it a quantum classical hybrid model of long short-term memory, which we call Q long short-term memory. In the study done by Samuel Yen Chi-Chen showed that Q long short-term memory offers better trainability compared to its classical counterpart, as it proved to learn significantly more information after the first training epoch that its classical counterpart learned the local future better, all while having a comparable number of parameters. For this reason, we could use variational quantum classical hybrid neural network technique on PD prediction. Data. Well, the data description, we have collected the historical data of the PD and macroeconomic, COVID-19 and change climate variables. In this section, our goal is to process the data necessary for the long short-term memory and quantum long short-term memory. The variables are, as you see, the PD, the high yield index, the inflation to 10 years, LIBOR 3 months, Standard & Poor's 100, and emissions of CO2 in the power sector. We identify the dependent and the independent variables. I mean, the target is obviously the PD, and the rest of variables the futures. Okay, something important is the data processing. In machine learning refers to the technique of preparing, cleaning and organizing the raw data to make it suitable for a building and training machine learning models. To process the data, we first split it into training and test data, where 2/3 of the data is used for training and the last third is used for testing. Okay, it's important to prepare for long short-term memory. Prepare the data in a sequence of past observations. The preparation of the LSTM on the time series data means that it uses a certain numbers of past observation to predict the future. In this case, the sequence length decides how many days the long short-term memory consider in advance. If the sequence is, for example, n, the long short-term memory consider the last n observation to predict the n plus 1 day. Okay, the long short-term memory model, then now we will explain the code to training the classical LSTM. Okay, we will use in this sense the simple structure that contain 4 neural networks layers in each LSTM cell. And there are the forget layer, the input layer, the update layer, and output layer. It's important to note that these 4 layers are the keys to building a long short-term memory neural network model that we can train and eventually use to predict. In the code, we train a long short-term memory to predict future PD and then test it on the test dataset. The learning rate is 0.0001 to obtain accurate results, and the number of the epochs is 20. The figure below shows the internal structure of an long short-term memory cells. The internal cells are denoted by CT, and LSTM updates, maintains or deletes cell state information using forget gate FT, input gate IT, and output gate OT, respectively. At time t, the input is the sequence vector xxt, hidden layer output ht-1 and cell state ct-1. Okay, we see now the results in each epoch, as you can see, in epoch 0, 1, etc., and epoch 20, that was the last. We then use the model to predict the data, the test set, and then compare the result of the prediction to the real values. Here we can see the real PD and the model forecast. In this graph, we can see the blue line is the real PD, orange line is the LSTM prediction, and the vertical line is when the test set start. We can see a good fit in the training and reasonable fit in the test. Here we can see the test loss graph and the train loss graph. This is the test loss and this is the train loss. Okay, now we start to talk about the quantum LSTM. I think the powerful quantum LSTM. To implement the QLSTM, we then replace the 4 key layers of the long short-term memory with variational quantum layer enabled in penny lane. The variational quantum layers are based on the following variational quantum circuits. This image is important to say it is taken from, and the other two taken from the quantum long short-term memory by Samuel Yen, Chi Chen et al. Penny Lane is an open source software framework from quantum machine learning and quantum computing with the ability to run on all hardware, meaning in digital and quantum computers both. Okay, in this image, the proposed quantum long short-term memory, the QLSTM architecture, each, as you can see, BQC, the variational quantum circuit 1, 2, 3, and 4 replace the neurons in the LSTM classical. Each BQC box is of the form as detailed in the figure. The sigma and tangent hyperbolic blocks represent the sigmoid and the hyperbolic tangent activation function respectively. Xt is the input at time t, Ht is for the hidden states, Ct is for the cell state, Et is the output, and we see other symbols like this that represent the wise multiplication or element-wise multiplication, and the element-wise addition, this symbol of sum. Just to remember, the element-wise multiplication operator computes a new matrix with elements that are the products of the corresponding elements of matrix 1 and matrix 2. Thus, the parameters to be trained instead becomes the rotational parameters within the circuits, hence forming a hybrid quantum classical neural network layer, as the optimizer is classical. The QLSTM is better because learn significantly more information than the LSTM classical. Those right after the first training epoch, as we can see later. And its loss decreases more stably and faster than that of its classical counterpart. And for this reason, we think that QLSTM has potential to be more accurate and learn more per epoch than its classical counterpart. In the following code, we proceed to train a QLSTM model to predict the PD time series, which will provide the QLSTM has advantage over the classical counterpart. The number of qubits in this case is just 4, related with the number of variational layer used is 1, and the learning rate is 0.01. Okay, just to before to start with the code, it's important mention what is the circuit, or what is the variational quantum circuit that we can use, and to explain, I want to show you this figure. and tell that it consists of 3 layers. The data encoding layer with the H. H is the Hadamard gate, R, Y, and R, zeta gates. The variational layer dashed box, that is the part from the right. In this case is the variational layer, and the quantum measurement layer, that are these symbols that we have here. Note that the number of qubits and the number of measurements can be adjusted to fit the problem of the interest, and the variational layer can contain several boxes to increase the number of parameters, all subject to the capacity and capability of the quantum machines used for the experiment. Okay, just to clarify a little, a quantum circuit is really a model of quantum computation, and it's similar to classical circuits, in which a computation is a sequence of quantum gates, measurement, initialization of qubits to known values, and possibly other actions. In other words, consists to in these circuits you can manipulate the metrics and obtain then the results that you are looking for. We can see now in this code that I am showing the detail and the on-train test and train loss, test loss, and the epochs is the same epochs that we use in the LSTM classical model, I mean 20, and we have this table that contain the PD and the model forecast are both, and now we will see the graph. This graph contain, in this case, the model, the Q LSTM prediction. We have the blue line, that is real PD, and half to the orange line, that is the quantum LSTM. And the vertical start the test set. And we can see a good fit in the train and reasonable fit in the test set. And now we can see the test loss graph and the test loss graph. Okay, now we need to compare between the classical LSTM and the quantum LSTM. In this graph we can see now three lines. The real continue is the real PD. The orange is the LSTM model, and the green is the quantum long short-term memory. And we can see the fit in the quantum LSTM model, and I think that is better just looking this is better than the LSTM model. But we need to compare with more detail, obviously. Okay, to compare the evolution of loss values, it will be very important. First, we see, for example, the train of loss. And we see in the graph of train of loss that the QLSTM learns much more information in the first few epochs as compared to LSTM, and that the result converges much faster as compared to its classical counterpart, although they both eventually converge to a suitable low value. This shows its improved trainability. Okay, similar to the training loss graph, we can see that for the test loss graph, QLSTM learns more information in the first few epochs as compared to LSTM as well as conversion. Okay, in this case, the Q is the orange line and the LSTM is the blue. And in I don't told in this is the same. The blue is the LSTM and this is the QLSTM that converge more faster, the QLSTM in this case. Okay, and finally, just to comment that the LSTM use more than 2 times number of parameters for training. Here, each 1,489, and here 665, the quantum. And then the LSTM use more than 2 times number of parameters for training, while QLSTM use comparatively fewer. This shows the advantage in trainability that QLSTM has over long short-term memory, whereas smaller number of parameters is needed. I hope you like the video. We see the quantum long short-term memory can be used to great effect for PD prediction, offering comparable results than its classic counterpart, while requiring significantly fewer parameters to train and getting more information per epoch. This shows that this technique has a potential in the banking world, since any time series data can be trained using a LSTM and hence also a QLSTM. At Fermac Risk, we have a wide range of financial risk training courses using classical artificial intelligence and now quantum artificial intelligence. This exercise is part of the IFRS 9 Credit Risk Modeling Level 2 course and the Quantum Computing for Credit Risk course. These courses have a duration of 40 and 50 hours respectively, and the number of exercises is over 100. These exercises are mostly notebooks in Jupyter with exercise in Python and R, like the one we saw. We have more than 15 years of experience training banking entities in Europe, America, South America, Africa, and recently Asia. We leave the links to the courses in this description, and wait for our next video of asset and liability management with Quantum. Thank you very much.